This is part of the Satellite Foundational course for JPSS, the Joint Polar Satellite System. This module discusses ways to use VIIRS imagery from SUMI-NPP, NOAA 20, and NOAA 21. I'm Scott Lindstrom from SIMS. VIIRS, the Visible Infrared Imaging Radiometer Suite, has superior spectral and spatial resolution to GOES-R's better temporal resolution. VIIRS' better spatial resolution is especially noteworthy as you move toward the poles. In addition, VIIRS includes a day-night band that allows visible imagery at night. Where can you find these data in AWIPS? If you look under the Satellite tab, scroll down and you'll see something that has polar in it. And it might list SUMI-NPP and or NOAA 20 and or NOAA 21 and or MEDOP-C. When you look at the Polar tab, you see the SUMI-NPP NOAA 21 or NOAA 20 tabs. You'll find imagery as shown here. The I bands 0.64, 0.865, 1.61, 3.74, and 11.45. Some of the M bands, and also the near constant contrast, which is the day-night band. This list shows what is discussed in this training. You might know of others yourself. Let us know. Light from the sun or from the moon can reflect off water. The bright region of sun glint or moon glint in satellite imagery can be used to infer surface properties. In this example from AHI, you can see internal waves in the ocean in regions of sun glint. An animation of this image is available at the link shown. For geostationary satellites, this works only near the equator, but polar orbiters can detect sun glint or moon glint in the day-night band in mid-latitudes or near the poles. Read more about this at the reference listed. Differences in moon glint, or in this case sun glint, tell you something about the state of the lake surface or the sea surface. When there are wind-driven waves, reflection is in all directions and water will look gray. Where the lake surface is flat because there is little or no wind, reflection is mostly in one direction and the water will appear darker. In mid-latitudes, the position of polar satellites with respect to the sun and the observation point allows these dark patches to be observed sometimes. A view of this image from GOES satellites showed no dark patch in Lake Michigan. This dark region has very light winds. When winds are light, the lake surface isn't mixing. Solar energy can heat up the surface, so in this case, you see warm temperatures as shown in the shortwave IR inset. The lack of mixing because of no winds allows a thin film of water on the surface to warm up. Observed sea surface or lake surface temperatures will warm considerably compared to adjacent regions where winds will mix surface and cooler subsurface waters. Of course, once the wind then starts up again, this warm patch will vanish as it mixes. Moon glint works just as well as sun glint in identifying regions of calm, if the day-night band gives suitable illumination. The dark region is one of calm winds. Day-night band imagery can also identify low-level circulation centers at night. This can be important for tropical cyclones if sheared systems have deep convection very much separated from low-level circulations. You really need to know where the surface center is when initializing forecast models. Here's an infrared image of a tropical system that is east of Hawaii. The precise location of the storm is vital for its insertion into a model. Where do you think the surface circulation center sits? Did you place it at that X? Now, of course, you might have been following it on the previous day and knew it was offset some from the convection. Do you see it in the day-night band image? All the convection is north and east of the surface center. Here's another example. Where would you expect the circulation center to be in this infrared window image from VIIRS? Did you imagine the circulation center to be where the X has been placed? The day-night band image reveals a distinct low-level swirl in the clouds. This is the center of this sheared tropical system. Of course, you typically don't operate without any other data sources. Perhaps microwave or the previous day's imagery showed you that the system was sheared. but the day-night band imagery here confirms what previous data might have shown you. Always use as much data as you can find. Here are two images of 2016's Tropical Storm Bonnie, infrared and day-night band visible imagery. The low-level swirl that is the center of Bonnie is masked in the infrared image by the cirrus clouds above it, but the cirrus is thin enough that it's easy to find the center of the system in the nighttime visible. Here's one more example of a sheared storm. In this case, only Earth glow is illuminating the cloud field, but you can still find the faint vestiges of a circulation center. Note also the streaks of lightning in the deep convection. Lightning shows as a streak because it is detected as it is occurring in just one swath. Here's another example over Hawaii. Calvin's center was at the southern edge of the convection as the sun set on GOES imagery. Day-night band imagery shows that its position didn't change overnight. In visible wavelengths, land is not very reflective. You know this because it appears quite dark in visible imagery, but land is a lot brighter in the near-infrared. There is more reflectance from grass and dirt in the 0.86 and in the 1.61 micrometer bands than in the 0.64 micrometer visible. Thus, vegetated features and bare ground will appear bright. This is important because water is dark, and the contrast between dark and bright means flooded regions can be more easily identified in the near-infrared. This example shows flooding on the South Platte River in Colorado shortly after torrential rains hit Boulder in 2013. The contrast between the reflective land and the water is very distinct. If you're familiar with the region and know what the river usually looks like, this is helpful in interpreting the scene. A bonus scene occurred on this day. This region benefited from two sequential passes about 90 minutes apart. So you can see the progress of the flood crest and maybe even calculate its speed. Multiple scenes are far more likely in 2025 now that there are 3 VIIRS instruments. It's a few days later. How far has the flood crest moved? Of course, clear skies help. Here's the view on the 17th, 3 days after the first view you saw. The flood has almost reached Nebraska. VIIRS data is also used to create a flood product, both from VIIRS only and also in conjunction with geostationary data. The website includes links to these flood products that cover the globe. This example shows flooding over southwest Louisiana. VIIRS has higher resolution than geostationary satellites. This is especially true as you move to higher latitudes. VIIRS is therefore better positioned to detect stratus and fog events in narrow valleys. The day-night band can give you information in the visible about the horizontal extent of the stratus, and the infrared can as well by exploiting the emissivity differences of water droplets at shortwave and long-wave infrared channels as found in stratus clouds. The brightness temperature difference field here shows fog and stratus starting to appear in the river valleys of southwest Wisconsin. That's in the orange and yellow enhancements. It's not quite there on the Mississippi, but it's forming. VIIRS can give an early alert to the formation of fog if the overpass is timed correctly. GOES imagery from the next morning shows more widespread fog locations. VIIRS has high spatial resolution, and if you have narrow valleys or sharp edges to the cloud bank, you are better able to describe exactly where the fog is present. Visible imagery at night, that is the day-night band on VIIRS, will view fog, clouds, smoke, and city lights. You can see fog in the valleys of southwest Wisconsin. Is there any fog over Chicago or Minneapolis? The lights of the city make it hard to tell. Is the feature spreading southeastward from the northwest corner smoke, cirrus, fog? You should interrogate other channels or products to discern that. In this case, the brightness temperature difference is showing stratus clouds over the river valleys of Wisconsin and over Chicago. The Twin Cities show no fog detected. The brightness temperature difference field will not detect smoke like it does low clouds and cirrus, so that feature spreading southeastward from the northwest corner is smoke from forest fires. Smoke detection at night is something that the day-night band, when there is sufficient illumination, excels at. VIIRS imagery detects fires. There are multiple shortwave infrared channels that can be used, and some have excellent horizontal spatial resolution, meaning small fires are detected. In addition, as mentioned, smoke from fires shows up in the day-night band. Here's an example of the Fort McMurray fires over Alberta way back in 2016. This is at 56 degrees north latitude, far from the GOES subsatellite point. GOES 16 pixel size here exceeds 5 kilometers, so small fires will not be detected. In this case, the fires were widespread and large by this time, but VIIRS better described the horizontal spread of the fire. In addition, the day-night band ably characterized the horizontal spread of the smoke pall, an important piece of information for air quality alerts. Here's a GOES East imagery about the same time. Only 1 pixel was very hot, and there's no information about the smoke. 1 week later, VIIRS sees smaller in area, fires that might not be perceived by GOES. The moon at this time is not providing sufficient illumination to show where the smoke plume is, but the visible light emitted by the fires is obvious, especially when you look at it in combination with the shortwave infrared at 3.75 micrometers. Here's another example over California. The thermal signature is readily apparent, and the horizontal extent of the smoke offshore is captured nicely. It can be trickier to monitor where the smoke is if it drifts over city lights. But you see the bright flare of the fire here and also the emitted smoke. You can also track how fires are evolving over time, as shown in these 2 examples from some famous fires. Note that in the animation, sometimes you can see the smoke, and sometimes you can't. It depends on the lunar illumination. True color imagery from VIIRS depicts the smoke very well during the daytime. In addition, there are smoke and fire-related products, such as aerosol optical depths. After the fires, VIIRS data can be used to detect burn scars. This is a post-grass fire burn over Kansas. There is a difference in reflectivity that the day-night band can capture. During the daytime, you can use the 0.86 micrometers from VIIRS to see burn scars. Compare the day-night band imagery here to the GOES 16.86 from the day before. In this case, there was no cloud-free daytime VIIRS view of the fire region. VIIRS data gives excellent views of ice leads in the oceans surrounding Alaska, very far from the GOES subsatellite point. Both infrared and visible imagery show where the cracks are, and the great temporal resolution at high latitudes allows for compelling animations. Here's a summary slide. VIIRS has excellent spatial resolution compared to GOES, and that resolution improvement is especially true the farther north you go. It complements the temporal resolution of GOES. Make sure you are using both. This concludes this training. Thanks for listening.